Moving to our next presentation, Zoe Learner Ponterio from SPIF. And I'm sure, Zoe, you're going to tell us what SPIF means.
Yes, indeed. So SPIF is the Spacecraft Planetary Image Facility at Cornell University. And that name tells you pretty much what we're all about. So spacecraft go out, they visit different places in the solar system, take amazing images and send them back to Earth. And so we are all about helping scientists and connecting the public with all of those amazing images. So I am so excited to be part of 2020. This is my fourth AstroFest that I've been involved in to some extent since I had this job, and I'm glad that it is still going strong. And so I'll go ahead and bring my talk up there. All right, so that looks good. All right, so tonight I am going to be speaking to you about the search for life. And so I named the talk Hunting for Aliens, Looking for Life in All the Right Places. And this is because we're going to focus on places we think we are most likely to find life, but it's important to recognize that we are still dealing with this data set of one. This idea that Earth life is all derived from one original life form, and we don't know anything outside of that. So ultimately, we're taking our best guess here. And before we talk about where we're looking for life, which is mostly what I'm going to talk about in the solar system, and later on, there'll be a talk on outside of the solar system, what are we doing to look for life? So this is just going to be like our little neighborhood talk, but it's good to start out with this question. What is life? Because if you remember from maybe even just a high school biology class, you hopefully were taught that this is not something that there is a universally everyone has agreed upon definition of what life is. So planetary scientists, and now we have people called astrobiologists, and that is something that is only a field about 30 years old at this point. And they have decided that as we go out for life, we're going to have, at least within our community, upon definition. So this is what we have come up with. 4 criteria. First of all, it is a contained environment. On Earth, this is the cell. It has to have control over the interior of that environment and somehow interact with the exterior of that environment. So in order for something to be alive, it has to be defined in space, right? It's got to be an object of some kind. All right, second is metabolism, right? It has to eat and produce waste. So it's got to use substances from the exterior that it's interacting with. It's got to have chemical reactions that produce energy that it then uses to do things in the interior environment. And then self-replicating, right? This is very important. It has to be able to make copies of itself using some kind of internal process. And this is often where viruses will fail this test. And whether or not viruses qualify as alive is hotly debated, and really, again, depends on what definition you're using. Under ours, viruses would not count. And it's because they fail actually 2 of these 3 I've already put up. They do not produce their own metabolism, and they cannot self-replicate. So as far as an astrobiologist is concerned, viruses are definitely biologically involved, but they are chemistry, not they have an effect on biology, but they're really advanced organic chemistry, not actually life forms. Now, this 4th one is one that people often don't stop to think about and isn't often included in standard biology classes, but planetary scientists have decided that it's pretty important, which is that it's not enough to self-replicate. You have to make mistakes. So this is evolution. We can't just have something that's making endless perfect copies of itself. It has to be able to make mistakes in those copies that produce variety. And then you allow just the natural selection of different varieties will be more successful in a given environment and therefore reproduce more and therefore become more populated. And the ones that are less successful will not reproduce as much, and their numbers will dwindle until they go away. So we are requiring Darwinian evolution as a criteria for calling something alive. It is important to note that people sometimes try and poke holes in this. A classic example, of course, is a mule. A mule is sterile. They cannot produce offspring, but they are definitely still alive. And I can say that because their cells can still replicate, right? They can still create new tissues within their own body. They cannot produce a macroscopic offspring, but that's okay. So we're really talking again on that cellular level of replication. All right, now going into where are we hunting? So that's pretty much the meat of my talk, is where are the places that we are trying to focus this search? And I did have to add a slide very recently to this, so let's just get it out of the way and talk about it. Venus. All right, so this slide, Venus was mentioned in this talk at the end, but I added a slide at the beginning, of course, because just a few weeks ago, there was this huge discovery. You might have seen headlines. We detected signs of life in Venus. So I really quick want to talk about what that was about, what we know and what we don't know. First of all, we did not detect life on Venus. That did not happen. What we did was detect phosphine, which is a molecule, and we detected it in the atmosphere of Venus. 2 different telescopes, so 2 different instruments detected this phosphine. And on Earth, as far as we know, there's only 2 ways to make phosphine. One is life. Certain microbes produce phosphine as part of their metabolism. The other way is by humans in a laboratory, and it's used in industry. So that is quite intriguing. Now, what we don't know is we do not know if there is possibly a way that phosphine can be created that we don't know about that doesn't involve life. Venus, after all, is very different from Earth, right? Much different environmental conditions. The authors of the paper that was the big breaking news where they released this discovery did do a cursory examination of, can we think of any obvious ways that phosphine could be created on Venus just with meteorology or geology or whatever, and they didn't find any obvious ways. However, the next steps are, of course, to think about this in more depth, to bring in all volcanologists, all meteorologists, all planetary scientists to sit here and brainstorm heavily on, okay, really, let's get creative. Can we explain this without life? And the second thing, of course, is we have got to get a probe to Venus that can actually go into the atmosphere and make direct measurements to confirm that this actually is phosphine and look for other things that could be signs of life. Because yes, there could be life in the atmosphere of Venus. It's not a great environment. High up in the atmosphere, the temperatures and pressures are pretty good, but the clouds there are made of a liquid that is sulfuric acid in a concentration of about 95%, I think, and the highest on Earth life can stand acidity is 5%. But we know that life adapts. So just because Earth life today wouldn't survive there now does not mean that there isn't life there. So don't rule out Venus, and let's get a probe to Venus. So now we're going to dive into our next planet on the list, which is Mars. Now, Mars, of course, has gotten attention for centuries since we've been able to really look at it through telescopes, and this idea of, could there be Martians? And honestly, until very recently, could there be Venetians? So, you know, the idea of Venus and Mars being close enough to Earth that either one of them might have beings living on them. We now know that no, there are no people-like things living on Mars, but we were always intrigued if there's any life at all going on. And our first step toward finding that out was, of course, going to the surface. And that was with the Viking 1 and 2 landers, which here pictured Carl Sagan was very involved in. And they were very ambitious. They carried with them a suite of instruments that were going to try and detect whether or not there was life thriving and very active in the surface, the immediate surface of Mars. So it landed, not our first planetary landing. We actually landed on Venus before we landed on Mars, which is odd, but we did that. So this was our second planetary landing. And this was our first view of the surface of Mars. Now, what happened here was that we kind of bit off more than we could chew. We thought we sent this great suite of instruments to answer definitively the question, is there life on Mars? And what ended up happening was, at first, it looked like some of those instruments were in fact detecting signs of life. But then people realized, Sagan being the one who quoted, extraordinary claims require extraordinary evidence, which means suddenly people said, wait, before we say it's life, we better really dig into things. And what they suddenly discovered was sources of possible contamination from Earth life, and also that some of the tests could produce results that looked positive, but were being caused by things that were not life. In the end, all tests were ruled inconclusive. So that means that they think they neither detected life nor did they fail to detect life. They actually didn't really do much at all to help us understand whether or not there was life in Mars. And this was a big disappointment. And actually, we pulled back from Mars for a while and did not go back for about 20 years when we finally built the Pathfinder lander with the little Sojourner rover hitching a ride. So this was launched and landed right after I graduated high school. So this was the first Mars mission I was really, aware of happening and seeing it unfold, and landed in July of '97. And you can see here, the little rover Sojourner was our first ever Mars rover, not our first rover overall. That was Lunicog on the moon, actually. We again found an interesting environment with some similarities, some differences to Earth, but again, obviously no teeming life just all over the surface. But intriguing nonetheless, signs that maybe it wasn't always like this. Maybe it wasn't always so cold and so dry. Maybe it once had liquid water on the surface. So we followed this up by saying, okay, instead of a lander with a little bitty rover, let's just make one big rover. And so this was the idea behind the Spirit and Opportunity rovers. If you know me, you know these are my babies, because these were the first mission I worked on, and I was on the science team for this as a graduate student at Cornell. And these are my girls. I love them. And of course, we know they were incredibly successful. And they were the ones that answered that question, was Mars ever warmer or wetter? Spirit went to Gale Crater and discovered all sorts of minerals and rocks that form in water. So finding things, salts and clays, and a lot of volcanic rocks, but clearly, like we see in Hawaii, lava that interacted with water. Opportunity went to Meridiani Planum and also found tons of evidence that there was once water here. There was once a vast sea here. First, we found evidence that was a sea that was very acidic and very salty. But then as we traveled, we found some older rocks that showed that, in fact, even farther in the past, the water was fresh, clean, drinkable water. So discoveries don't happen overnight. Right? Nothing just all of a sudden overnight, press conference, we discover this. That's not how the discovery of alien life, if it happens, is going to happen. That's not how the discovery of past water on Mars happened. It takes years. And so these rovers were really the ones that over the course of their many years did answer this question. And now today we accept as scientific fact that Mars was once warmer and wetter and did possess environments that are considered habitable by Earth life standards. Well, these rovers worked so well that we just did it up and we created the biggest rover that we possibly could land on Mars with our current capabilities. This is the Curiosity rover. As you could see, it's the size of either like a compact SUV or a really big car, I suppose. It's 1 ton. All right, it's 9 feet wide, 7 feet tall. It's huge, usually bigger than a lot of people think it is. And this one went to Gale Crater. It's still operational there 8 years later, going strong and studying again layers of ancient rock, finding more evidence of liquid water having interacted with these rocks over long periods of time. So what we have now is confirmation that, yeah, Mars was definitely once a habitable environment by Earth life standards. So we're on our way now, and later tonight you're going to hear all about the Perseverance rover, pictured here, that is on its way to Mars right now, landing February 18th next year, coming up fast. And it looks very much like the Curiosity rover in size and design as far as the wheels and everything, but it has a whole new suite of instruments, which I think you're going to hear a lot about. So I'm not going to spend a lot of time on that. I'll just say watch the keynote speaker for that. But this is a rover that is going to be the first step in actually picking up, after our horrible defeat with Viking, of can we detect life on Mars? Now, one of the things that I know I get asked, because I asked myself, will this rover be able to detect life, either past or present? And the answer to that is, in and of itself, probably not. But what this rover is going to do is carry the most sophisticated suite of instruments to look for evidence of life. Remember, evidence doesn't necessarily lead immediately to conclusion, but to find things that look promising and to cache them as samples that we will then go and collect and bring back to Earth. I think that most scientists feel that, in Sagan's words, extraordinary claims require extraordinary evidence, that we're really not going to feel comfortable coming out and saying, yes, there was life on Mars or is still life on Mars, without having actually gone at the stuff in our labs here on Earth. So I have a feeling that we're going to see very enticing information from this rover. Is it possible that they will see something so obvious that they will say, okay, come on, that's got to be life? Yes, possible. But it's important to know, like, this is part of a long process of Mars sample return that's going to be going on over the next decade. Now, this rover is landing in Gale Crater near this beautiful formation that, yeah, it's just what it looks like. That's a river flowing into the crater, and it has formed a delta. We know that deltas form over long, sustained periods of flow. So this was not just one big flash flood. And also, we have these on Earth, right? Here's the Mississippi Delta. And one of the things that's great about deltas is they're an awesome place to preserve any evidence of life that was in that river or in a lake that used to fill the crater. And the great thing about Jezero is that the rocks that might hold that evidence are both well preserved and easily accessible. That's a rare combination. Usually if you're well preserved, it's because you're buried deep underground. And if you're exposed and easily accessible, you've been like that for a long time, and there's contamination and alteration by the current environment. But because of the erosion happening here specifically, we think there's a good chance that we'll get some pretty pristine samples that are accessible to the core sampler on Perseverance. Now, while we've got this beautiful picture up here from Earth, let's take a moment to talk about Earth and the search for life on Earth, because that is still a thing. We are still discovering new life on Earth. And we have to remember, again, it wasn't that long ago that a lot of the life that we take for granted now, we had no idea about. And the one I want to focus now is on the deep ocean. So in 1977, not that long ago, honestly, we had our first expedition to the deep ocean floor. And what they were thinking they would find would be some interesting oceanography, geology, and these were the kind of people they took with them on this team. The kind of person that was not anywhere on this team was a biologist. None. Because everyone had just come to the conclusion that the bottom of the ocean would be a desert. There would be nothing living down there. The pressures were too great. It was too cold. There was absolutely no sunlight. And so they were like, oh, there's not going to be any life down there. And of course, they went down and got a call from one of the people down in the submersible. He said, yeah, I thought you said there wasn't going to be any life down here. And they're like, yeah, that's right. And he said, well, there's stuff swimming and crawling around. So maybe we were wrong. And some of the people on the boat actually thought that this person was hallucinating because of the pressure. That's how certain they were that there wouldn't be life down there. Now, we now know that the bottom of the ocean is teeming with life, especially around these hydrothermal vents that we see pictured here, the black smokers, they're known. And this is the last place some people thought they'd see life. That water is 600 degrees and acidic and full of sulfur and things that we normally think of as toxic to life. And yet, stuff is thriving all around it. This is an important ecosystem on the Earth. And if you'd like to know more about this, it was made into a really excellent National Geographic video, Dive to the Edge of Creation. Now, creation? What are they talking about there? The discovery that life was down here at these deep sea vents sparked a controversy that is ongoing. And that is, where did life start on Earth? Prior to this discovery, everyone was kind of on board with the idea Darwin put forth, the tidal pools, the warm, soupy beginnings, something that had access to sunlight and would be photosynthetic, but still, yes, water-based. But when they found life around these hydrothermal vents deep in the ocean, they realized that this was an environment that was far more protected. And with all the amazing climate changes that Earth has gone through, that this environment would be far more stable. And wondered if maybe this is where life got started. And maybe the first life was not photosynthetic, rather chemosynthetic, which is what the life here is. It doesn't need sunlight at all. That raised an important question, because when we are hunting for aliens, it's important to distinguish two things. There's the environment that exists today, and then there's the environment of Genesis, this idea of what was the environment that life started in. And we know that here on Earth, with all the changes Earth has gone through, that the environment in which life started on Earth most likely does not exist on Earth today. Life has evolved to inhabit every single environment on Earth and has adapted through all of the changes that Earth has gone through. But that Genesis environment may very well be lost to ancient times and no longer exist. So this is a problem when we're going out and trying to hunt for life. What are we even looking for? You might say, oh, well, look for places that seem like places on Earth. Well, that's not exactly comparing apples to apples. Even if we find some place that has a similar environment to Earth now, that doesn't mean that that place ever had that Genesis environment, because we don't even know what that was here on Earth, and we're pretty sure it probably doesn't exist anymore. So this becomes quite the conundrum. But one thing that did really get exciting then with this discovery was just a few years after that, when we realized that Jupiter's moon Europa was hiding an ocean underneath its surface. So this is Europa, and one of the things that really stands out about its surface is there's almost no craters. Craters tell you how old a surface is. This surface is amazingly fresh. In fact, recent calculations put the last major resurfacing event at only 70 million years ago. And I know that that may seem like a long time, but let's keep in mind that the solar system is 4.5 billion years old. So 70 million, that was like right when the dinosaurs were about to meet their end. That is not that long ago on the scale of the solar system. So this surface is very fresh and there's cracks in it. The surface is made mostly of water ice. And when we flew by instruments, this was the team that worked on the Galileo spacecraft, we were able to pick up the anomalies in the magnetic field. So Jupiter puts out this huge magnetic field, and that magnetic field interacts with Europa. And then we were picking up an induced magnetic field around Europa. That only happens if there's something inside Europa that's electrically conductive, right? Something that can conduct electricity. Well, ice doesn't do a great job at conducting electricity. People said, okay, Earth has a solid crust of rock and a liquid rock mantle. Maybe it's got a solid water crust and a liquid water mantle, an ocean. But furthermore, pure water also does not conduct electricity very well, but salty water does. And the amount of magnetic anomaly they measured did match up with a subsurface salty ocean about the same salinity as oceans. And furthermore, what's keeping this ocean warm is the same thing that causes all the volcanoes on the innermost moon, Io, of Jupiter. So we see here that as we go around Jupiter in normal tidal from Jupiter's gravity actually squeeze and push on the moon, and that creates friction inside, which heats up the inside. So not only do we have a solar, it's also likely got hydrothermal activity at the base of the ocean, just like Earth's ocean does. Now, we're under a few miles of ice, but honestly, we're already pretty far out from the sun. The lack of sunlight is not necessarily a problem. As we saw, there's life on Earth that doesn't require sunlight. So we very well might have an environment here that is very much like an environment we know life to inhabit here on Earth. Furthermore, there's the chance that that environment is also very close to what we think the Genesis environment might be like, depending on whether you want to argue where life got started on Earth. So that's the question. If life did require tidal pools, then yeah, the fact that Europa has an ocean that looks like our oceans now doesn't mean it's going to have life, because Europa certainly never had tidal pools on its surface. So that's an example of it could match an environment we've got here and yet come up completely sterile. However, if life did start in the deep ocean, then we might have something that matches that environment. And let's remember, just because that's not how life gets started on Earth doesn't mean it's not how life could start somewhere else. So maybe Earth life started in tidal pools, but that doesn't mean that life couldn't start in a deep ocean. Who knows? But this is intriguing in that it does match a known habitable environment very well. So what are we doing to find out more about Europa? Well, we are sending a spacecraft. Europa Clipper is slated to launch sometime in the mid of this decade, and it is going to orbit Jupiter. Jupiter's gravity makes it pretty hard to go into orbit around one of its moons. Furthermore, you don't necessarily want to do that, because Europa is close enough to Jupiter that huge magnetic field is not great for spacecraft electronics. So the Clipper name comes from the fact that we're going to orbit Jupiter in a highly elliptical orbit, very oval orbit, and we're going to clip past Europa with every orbit that we slingshot in and around Jupiter, so that we don't stay in that magnetic field for very long. We dip in, we take some quick measurements, and then we get out where it's safe. We hang out there, transmit back to Earth, and talk to the scientist and figure out what do you want to do on the next pass. So it's going to clip past Europa really close. The closest planned clip at this point that I've heard is 25 kilometers above the surface. That's just 18 miles above the surface. So we're going to get really close. Now, what can we possibly tell about an ocean if we're just drifting past it in space? Well, again, we see all those cracks in the surface, and what we think is happening there is in the chaos regions, that these are hotspots. We have hotspots here on Earth. We have the Hawaii Islands. We have Yellowstone. Those are hotspots. Something similar here could mean that there is recent upwelling of water. That here we might be able to find on the surface ice that is recently brought up from the ocean underneath, and therefore, even though if there's life, it wouldn't still be alive, all of it might be preserved in this very fresh ice that is only recently been ice and was previously ocean water. Now, of course, we want to do more. And so, yes, we are already coming up with the concept mission of landing on Europa. As I said, this is especially tricky considering the high magnetic fields and radiation coming from Jupiter. So we got to figure out how to have a spacecraft that can actually survive and stay at Europa, but we want to do it. I do want to point out, if you look at their logo that they've come up with, that is supposed to symbolize the lander sampling the water coming up from inside and having little maybe organic bits or cells or something in it. But if you've seen the movie Europa Report, this might make you think of something else. They just kind of laugh and say, yeah, okay, could be a tentacle, but oh well. Moving on. So that's Europa, which looks really intriguing. All right, and we found out about that. All right, let's now fast forward to the year 2000. Deep sea exploration now has been chugging along for a few decades, but we discovered yet another kind of environment. This is known as the Lost City, and we've now identified a few other environments like it. And this is what we call white smokers. So this is a hydrothermally active environment, but it's not as hot as those black smokers. So this is a little more of a simmer than a boil. It is still a place where hot rock is in contact with hot water, and an exchange of nutrients happens that's able to sustain an ecosystem. So again, notice that there's not like, you don't see a ton of fish and stuff floating around here, but there is life here and it's being sustained in this environment. So we're like, okay, so hydrothermal vent life, can look like a lot of different things. But then in 2004, the Cassini, oh yeah, I wanted to mention this also is available if you want to see more about this in a great video called Aliens of the Deep. I don't know if it's still there, but a little while ago I saw that it popped onto Disney Plus. It was made by James Cameron, and it's a really good video on this discovery of the lost city. All right, so in 2004, Cassini arrives at Saturn. All right, now we knew that Saturn had a lot of icy moons, medium-sized icy moons, much smaller than Europa. So everyone kind of assumed, they're probably frozen solid. They did have fractures that were seen by the Voyager spacecraft, but it's kind of assumed that that was long in the past and not any kind of sustained tectonic activity. But we want to notice this dot in the fuzzy outer ring here of Saturn, and that is the moon Enceladus. And when the Voyager spacecraft flew by, Enceladus was one of these many medium-sized moons. In fact, kind of, on the small side, not anything interesting. But when Cassini got there, found out that the reason that that fuzzy ring is there is because Enceladus is making it. We suddenly realized stuff was shooting out of the South Pole of Enceladus. And so when we got close with Cassini, we saw that here was a surface that is the most reflective surface in the solar system. This is like blindingly fresh snow, bright surface. And again, we see lots of areas where there's practically no craters and lots of fractures instead. And out of those fractures is coming this spray of stuff. And we were actually able to fly Cassini through these plumes of material to check out what they were. And this is just a really cool animation of what it might have looked like if you could have been sitting off watching the show as Cassini flew over these plumes through this material, was able to touch it directly with its instruments. And sure enough, it's water. So it must be coming from a reservoir of water underneath the surface that's being put under pressure. And it's salty. And bar chart that you really want to just focus on the word organics, carbon-based organics. Now that does not mean life, that means the ingredients, the building blocks of life are present in this water. So now a couple questions remain. One, is this just like an underground lake, or is this another global ocean like Europa? And two, how long has this been going on? Is this just a transient effect, or has this thing really been going like this for a long time? Now, this moon is small, understand. They were pretty shocked to find that, in fact, there is a global subsurface ocean, not just a little local lake reservoir. To give you an idea, Europa is about the same size as our moon, which is only a little smaller than the planet Mercury. But Enceladus is much smaller than that. So if our moon and Europa were the size of a soccer ball, Enceladus would be the size of a ping pong ball. So we were really surprised that there's enough internal heat it can hold on to sustain the liquid water without it freezing solid. How is this possible? It turns out that we didn't, we underestimated the effects of the other moons tugging on Enceladus. So at Europa, we think of Jupiter as the main force that's pulling on Europa, giving it its ocean. We didn't think Enceladus was getting enough of that from Saturn, but it turns out that you add that together with all the other moons tugging on it, and you do get enough energy to do this. All right. So thinking back to the lost city, those white smokers here on Earth, remember I said they weren't as hot, right? This is a smaller moon receiving less energy, so similar thing. It's not as hot probably at the base of this ocean, but we do believe the base is rocky because Also in those plumes, we detected silicates, right? That's what rock is made of. So we know that that water is interacting with rock, and therefore there must be a boundary at the bottom where there's that hot water, hot rock interaction happening, which reminds us a lot about that white smoker environment on Earth. Now, if you love chemistry, dig into this. If you don't worry, I'll tell you what you need to take away from this. And the key word there is serpentinization. You can walk away today having said you learned a really cool word, serpentinization. And the reaction here is basically hot rock, hot iron silicate rock, contacts hot water, they react and form an iron oxide called magnetite, so a different kind of rock. They also happen to form quartz, that's where the silicate goes, and then they produce hydrogen as a byproduct. And what can you do with hydrogen? That turns out we know exactly what you can do with hydrogen because they're doing it at the Lost City. Microbes are eating it. So this process happens at the bottom of Earth's oceans. This serpentinization happens, it produces the hydrogen, and then things eat the hydrogen. We detected this hydrogen in these plumes. So we know between that and the silicates that serpentinization is happening at the bottom of Enceladus's ocean. Does that mean something's down there eating it? Well, ironically, the fact that we found the hydrogen would suggest the answer is no, because if something were eating it, it wouldn't be there. However, maybe there is some other process that is limiting the amount of life so that it doesn't eat all the hydrogen. On Earth, the life tends to eat all the hydrogen. That tends to be what holds the ecosystem at its limit. But maybe that's not what does it on Enceladus. So again, it's a bit inconclusive. We at least know there's food down there. There is a food source for that metabolism. Now, at first, people were really pulling their hair out because, of course, nobody had thought of Cassini as a life-finding mission. It was going to Saturn, okay, way outside the habitable zone. They really did not anticipate this. And the instrument it used to make all these measurements was much more about finding small molecules, not big, complex organic molecules, things like amino acids and proteins that would be even more exciting. But, of course, scientists are clever. And they did find a way to tweak and tease out data that they didn't previously think they could. So this is along this slide, but the main takeaway here is they were able to conclude that there were larger organic compounds. So things beyond just simple few molecules, things that were far more complex. So we definitely know that there's organic chemistry happening here. We found another environment that matches something we have here on Earth. And we also found that it looks like this ocean at least could have been here since the beginning. Some models say that it freezes and thaws on a cycle. That wouldn't be great for life, but we know life here on Earth can survive being frozen and then thawed back out. So that doesn't mean there's no life, but that is still an open question. Does Enceladus's ocean stay there all the time, or does it come and go? Well, now, as you can imagine, the people who study Europa, and by this point, Europa Clipper was already something that was going to happen, were kind of disappointed because the thing that Enceladus is doing that's so awesome, of course, is it's spraying this ocean out into space. You don't have to land. You don't have to worry about drilling through the ice. It's just putting it out there for you. Cassini flew through it and able to make measurements. So it'd be super easy to directly sample and measure this ocean, a lot easier than Europa, which doesn't seem to be doing that. So they were kind of like, well, shoot, we all set to go to Europa, and now we've got this other target, which almost kind of looks like it'd be better, but we're already committed to going to Europa. Now, this is one of those cases where just because it's old data doesn't mean it's not useful data, because now that we knew plumes were a thing, people dug back in to that Europa data. They said, hold on, anyone remember that there was this weird magnetic anomaly that we actually were never able to explain? It was just this little effect. And everyone's like, yeah, I remember that. I said, you know what would explain it is if there was a plume that Galileo flew through and we just didn't get pictures of it, so we didn't realize it happened. They went, yeah, that would kind of explain that, wouldn't it? And sure enough, they looked back at some images and they're like, Could that be a plume? Those few bright little pixels? Maybe. So there's suddenly at least the possibility that Europa might also have plumes that just aren't as large and not as constant as Enceladus's. But now the Europa Clipper people are hopeful that maybe they'll get lucky like Galileo did and just happen to fly through one. Now, we still do not know for sure that Europa has plumes. This is still a hotly debated topic. I have met people that are like, it's obviously has plumes. And I have met people that are like, I'm not convinced yet. So this is still debated. Europa Clipper is hopefully going to answer for us whether or not Europa has plumes. And obviously, we really hope it does, because that'd be awesome. And now we're going to go back to Saturn, though, talk about this moon, Titan, Saturn's largest moon. It's bigger than the planet Mercury. And what you see here is all we could see from the Voyager images, just a fuzzy orange ball, because this moon is unique in that it has a very thick atmosphere. Thicker than Earth's, 4 times the density, and the pressure is 50% higher. So you get the same pressure if you go to like the bottom of a swimming pool here on Earth. And that atmosphere, rather than something like Venus's with, sulfuric acid, is actually the rather inert nitrogen, the same nitrogen that we have in our atmosphere. And what the orange fuzz is, it's an organic haze that covers the whole moon, and we can't see through it, at least not with the kind of cameras we took with us on Voyager. So this was very intriguing. We detected that there was methane in this atmosphere, and that these oranges were organics. Other than that, we knew very little about Titan until Cassini got there. So when Cassini got there, we finally got some images of the surface. We were able to map some features using infrared light that could see through the haze. We also, of course, sent a probe. The Huygens probe descended through the atmosphere and got through the haze and provided the first ever pictures of the surface from below. And what we saw, was something that looked just like a river channel. And sure enough, that's exactly what it was. Some people had predicted this, but it was kind of considered a bit fringe until we actually got there and saw that it was truly happening, which is liquid methane on the surface. So that methane in the atmosphere is at about 5% humidity. And it turns out that with those pressures and the temperature, which is around negative 300 degrees, that is at the triple point for methane, just like Earth hovers around the triple point of water. So methane does condense into clouds, it rains, collects in rivers, and flows into lakes and seas, as we see here. The dark region is a methane sea, and these things are as big as our Great Lakes. And so this is a place that has a hydrologic cycle like the Earth. The surface here is not rock, it's water ice. But what we see here is that a lot of the geology seems to work the same way, right? Instead of liquid water, it's liquid methane. Instead of solid rock, it's solid water. But things seem to carve out canyons and form mountains in a lot of the same ways that it does on Earth. So this is like Earth 2.0, right? This is a different Earth with a lot of the same processes happening. Now that atmosphere also, which is mostly nitrogen, and then, like I said, about 95% nitrogen, 5% methane, and then a little bit of carbon monoxide mixed in, is pretty much what we think Earth's first atmosphere was like. That atmosphere has been altered significantly by things like volcanic activity and then life, producing the atmosphere we have now. Titan seems to, though, have been frozen in time, and that it stayed that way, probably because it was colder. So this gives us a natural laboratory where we might be able to see what those early conditions were on Earth before all of this happened. So this could be our way to see what did Earth start out with. And then there's the really freaky idea of we have been all about follow the water with life, because all life on Earth is water-based. It's the one thing that we see that life seems to need. Anywhere there's water, there's life. That fills the cell. But what if life doesn't need liquid water. What if it just needs a liquid of any kind? And there's a liquid here, methane. Could you have life that had a base of liquid methane instead of liquid water? Turns out there are a lot of challenges with that. For one, water is a highly polar molecule. It means it dissolves things really well, so you can have all sorts of nutrients and stuff floating around in it. Methane does not do this very well. It does do it some, but it's not nearly as good as water at it, but that's not enough to rule out that this could happen. All right, so another interesting thing is Titan also has a subsurface water ocean, just like Europa does. And impact craters are places where we could have punched through the surface, brought up fresh stuff from this, and had it interact with the organics on the surface. And who knows what kind of crazy organic chemistry happened there. To investigate this, we are in the process of building and getting ready to send the Dragonfly mission. And this will be a car-sized quadcopter drone. Because again, Titan has a thick atmosphere and 1/7 the gravity of Earth. So this is a super easy place to fly. So why send a rover when you can send a drone? And so it's going to hop, skip, and jump around the surface of Titan. And those impact craters is one of the things they hope to go and explore to see what kind of chemistry happened shortly after the impact, when you had warm water and all those organics in contact with each other for an amount of time. So to sum up, I'm going to put up my final slide here. And if you get the movie reference here, you are near and dear to my heart. If you don't, I will clue you in. Oh, bad pun. This is the 1985 classic movie Clue that was based on the board game. Yes, the board game came first, and then they made this movie. And if you have not seen this movie, please do. It is a classic. It is hilarious. I've covered up a lot of the stars' faces here, of course, but this is a star-studded cast. But it also is this idea of this mystery and who's actually responsible for life, maybe more than one life. So this is that kind of, we've got our suspects lined up here. And we see that we've obviously got Mars here and Europa and Titan and Enceladus, but I've also thrown in Venus. And honestly, there's a few others here. Neptune's moon Triton is clearly active and might have an ocean subsurface. Pluto has evidence of having liquid water under its surface. So if liquid water is what you need, we can't rule out these guys as well. So that is basically a rundown of the environments where we think we might find life and where we are either looking or planning to look. And I think we got time now for some questions.
All right, let's see here. Actually, you want to unshare your screen and we can see your background. What, just as a matter of interest, what is your background?
So this is a colorized version of the New Horizons parting shot of Pluto. So that was a grayscale, but someone colored it to be what we think the surface of Pluto actually is. It does have a blue sky because that is a nitrogen atmosphere like ours. So.
Right. All right. Let's see here. You've Nicholas Gadash, actually one of our educators here. You had actually done a presentation for his students through one of our summer camps this summer, and he asked about amino acids. I'm not exactly certain what he was specifically asking about, but maybe if something connects to amino acids you want to share with that.
Right, so amino acids are what our bodies use to build proteins out of. And of course, proteins are everything for our body. It's how we build tissues and how we send messages and tell our body to do things. So amino acids are the building blocks. They are what the DNA actually codes for. That's what DNA does. It codes to build amino acids strung in a specific order to make different proteins. So that is considered a kind of medium-full organic compound. It's definitely more complex than something like, methane, but it is not as complex as something like DNA. So it's kind of middle there. We have found amino acids out in space. Interestingly, we detected them on a comet. So that we know that one amino acid that our body uses, glycine, does not need liquid water to form, and that is exactly the one we found in a comet. As we find in nature, if it can happen, it does. So glycine can form with liquid water, and it indeed has formed out in space. So that means that something like glycine could have even been delivered to the surface planets and moons, and therefore provided that building of those ingredients needed. So amino acids would be something we would really want to try and detect if we brought Mars samples back, or if we were going to land on Europa. The instruments on Dragonfly are being worked and finalized, so I don't know if they'll have the capability to detect that, but certainly going to be looking at what kind of organic compounds are on the surface.
All right, great. No additional questions as of yet, so actually,
Patrick has a question.
actually, I think Patrick mentioned, he said, is it possible for amino acids found in carbonaceous chondrite meteorites tie back to your points on amino acids?
Right, so there's actually quite a debate raging right now between how did Earth and obviously all bodies in the solar system get seeded with the ingredients for life. The idea being here that the initial planets and moons, when they form, are very hot, and organics tend to be volatile and high temperatures. So the idea being that after the surface is cooled off, these volatiles had to be delivered after that. Comets are one possible source, and they do carry a lot of water with them, but asteroids also have water as well as organics and these other ingredients. I think the most simple thing is to say it was a combination. There's a lot of it was asteroids that gave us life in oceans. It was comets that gave us life in oceans. They were both crashing into Earth, and they both have all of them. So they've likely both played a role. Exactly, what the split is, that'd be something interesting to find out. So.
All right, let's see here. Phil asks a question about instruments that could go to Mars, which, again, we've got Nagi Cox coming up, so we'll sort of table that question for now. I think it's more of a generic Mars question. Gashabeka says, why is Mars red?
Oh, classic question. The red planet. And why is that? The simple answer is that it's rusty. Mars has a lot more iron in its crust than Earth does. Because it was smaller, it didn't differentiate as much as the Earth. So even though most of the iron did end up in the core, like Earth, more iron stayed in the crust on Mars, had much weaker gravity. And over time, that iron has oxidized, right? We now know that Mars used to have water and possibly even an oxygen atmosphere, but that has reacted over billions of years to form oxidized iron everywhere on the planet. So It is rust.
All right, one last question here is, could there be a water ocean beneath the crust of Titan?
So we definitely think that there is. And it's one of those that, I mentioned it very briefly, and it gets overlooked because the atmosphere and the surface of Titan is so interesting. And it's kind of like this afterthought of, and it likely also has a liquid water subsurface ocean like Europa's. So Titan literally has the possibility of having two biospheres. If you think about it, there could be Earth-like water-based life underneath the surface, and then totally not like Earth life, methane-based life in the lakes and seas on the surface. I mean, can't rule that out, which is really crazy to think about. But yes, Titan also has an ocean. We don't know for sure if that ocean has hydrothermal rock activity at the base of it, though. So Titan orbits quite far out from Saturn, doesn't get a lot of that tidal action. So might not have that same kind of hot rock energy that Enceladus and Europa have. But yeah, measurements indicate it does have an ocean.
All right, great. Well, I want to thank you again for coming down here or virtually coming down here to join us for AstroFest. Maybe if you could take 30 seconds or a minute, maybe talk a little bit about SPIF and the work that you do, and and the resources that SPIF offers the public.
Sure, I'd love to. Thanks for giving me the time to do that. So SPIF does a lot of work providing planetary science themed outreach throughout the whole central New York region and focusing on the solar system and space exploration. We visit schools normally and places like Copernic, libraries, museums. So obviously the last few months we've had to change drastically how we do this because we definitely didn't want to stop doing it. So we developed the Shelter in Space Remote Learning Program. And so this is basically trying to do SPIF work at the K-12 support and out public reach. And so if you go to the SPIF website or to the SPIF Facebook page, you will see links all over the place to the Shelter in Space portal. You can contact us and we can set up a virtual event with your community center or your classroom. And there's all sorts of possibilities with remote activities together or have live Q&As. And we're trying to do all of this as much as we can virtually available. We started a YouTube channel, so you can pop over to that sometime, check out some of the videos we've made there. So yes, we're reinventing what SPIF does, but we're still trying to be there to get all this wonderful discovery and information out there to the public.
All right, well, thanks again. I really appreciate the time you spent with us here, and we will now actually going to translate to a little advertising here, and we'll say so long to Zoe, and so we'll see you next time.